Greetings, class. For this segment, I'm going to refer to the t-table in SPATS some. So if you have your book handy, it would be a good idea to get a hold of your book. Although I have also posted the t-table online in previous week's material. So go ahead and have that table handy. This segment is all about using that table in order to choose the correct t-value, table t. When it comes to choosing the correct t-value from the t-table, you need to know two pieces of information. One of them, hopefully, you're already familiar with, the degrees of freedom. And we calculate the degrees of freedom the same way we were before with confidence intervals, n-1. So however many cases you have, that's your sample size, that's n. If you subtract 1 from that, you have your degrees of freedom. I'll come back to that sheet in a second. And as you also may recall from your work with confidence intervals, the degrees of freedom will dictate the row from which your table t-value will come. Table t. All these t-values in the middle are table t-values. So the first thing you need to know is just like before, and that is the degrees of freedom. And degrees of freedom, when we are conducting a t-test for one sample, are calculated using the formula n-1, the number of cases in our sample minus 1. Now, back to this sheet. The second piece of information that you need to know in order to choose the correct value from the t-table is the task at hand, which you're hopefully familiar with that phrase, task at hand, because I used that phrase, task at hand, in order to refer to the calculation of confidence intervals. And so far, up to this point, calculating confidence intervals, that is the first row on that t-table, calculation of confidence intervals. And you can see you have options 80%, 90%, 95%, and so on. Well, now the task at hand gets a little bit more complicated in order to choose the correct t-value. When it comes to t-tests for one sample, so we're done with confidence intervals for now, in a manner of speaking. When it comes to a t-test for one sample, the task at hand will involve two pieces of information. Whether or not you need to conduct what's referred to as a two-tailed test or a one-tailed test. Okay, two-tailed test or a one-tailed test. And also the size of the tail of the distribution. Now the tail has a couple of different names. The tail of the distribution is also referred to as the critical region. It's also referred to as the rejection region. And it might be easiest to refer to the tail of the probability distribution as the rejection region, because it is that region, it is that part of the probability distribution that will help us determine whether we should retain means keep, or believe in, whether we should retain a null hypothesis or reject, do away with, discard a null hypothesis. And again, when we are conducting t-tests for one sample, what we're really doing are conducting tests of a hypothesis. And as such, based on your analyses, you are going to have to make a firm determination whether or not you are going to retain or keep or believe in a null hypothesis, or you will need to decide if you should reject, discard, or not believe in a null hypothesis. So as you can probably guess, it's pretty important to have a pretty good handle on what hypotheses mean and what they are. Null hypothesis H sub 0 versus research hypothesis H sub 1. So in sum, these are the two pieces of information you need to know in order to choose the correct t-value from the t-table. And those two pieces of information are the degrees of freedom, n-1, and the task at hand. And in order to determine the task at hand, you need to know whether you are conducting a two-tailed test or a one-tailed test, and you also need to know what the size of your critical region or rejection region or tail should be. Now, how do we know whether we're conducting a one-tailed test or a two-tailed test? Well, let's start here. If the hypotheses, and remember, hypotheses come in pairs, H sub 1 and H sub 0. H sub 1 is the research hypothesis, H sub 0 is the null hypothesis. If hypotheses specify direction, you need to set up and execute a one-tailed test, direction. If the hypotheses, the way they are worded, that's what we're talking about. If the hypotheses specify direction, you will need to set up and execute a one-tailed test. If your hypotheses, and again we're talking about the pairs, if your hypotheses do not specify direction, if they simply say different, you need to set up and execute a two-tailed test. So if the hypotheses do not specify direction, if they simply state that two things are different from one another, they don't say higher, lower, faster, slower, anything like that. If they don't specify direction, you will need to set up and execute a two-tailed test. Now, what does that mean? Here, I have a couple of different sheets. And this is available on Blackboard. Actually, I'm making everything available on Blackboard, so feel free to print out the handouts and refer to them, so you don't have to pause and copy this whole thing down. But these are some examples of hypotheses that would require a one. Excuse me. Start with two. These are examples of hypotheses that would require a two-tailed test. A two-tailed test. So I'm going to read them and point some things out to you. This one is referred to as example A, and I have labeled these as example A, example B, example C, etc. Because I'm going to also do a drawing later on. Okay? So example A, H sub 1, the research hypothesis. UMKC freshmen will study a significantly different number of hours per week than the national average for college freshmen. Population mean equals 9.2 hours. So again, the research hypothesis, UMKC freshmen will study a significantly different number of hours per week than the national average for college freshmen. The population mean is 9.2 hours. The null hypothesis is simply H sub 0. UMKC freshmen will study an equal or same number of hours per week as the national average for college freshmen. Population mean is 9.2 hours. Now, direction was not stated in that hypothesis. It simply said significantly different or equal / same. Significantly different or equal / same. So what does that mean? That means that according to our hypothesis, we are going to, this one right here, example A, we are going to be comparing UMKC freshmen, that's our sample, to the entirety of college freshman population. And the college freshman population studies 9.2 hours per week. We're going to compare our sample mean, which we don't know yet, to that population mean. How would this look like as the probability distribution? Well, let's assume we were asked to test the hypothesis at the 0.05 level. That 0.05 level, that is the size of the critical region, the rejection region, the size of the tail or tails. If we were asked to test that first example, UMKC freshmen will study a significantly different amount than the national average. if we were to set up this probability distribution, and you're going to be asked to do this very same thing for a lot of the problems that you're going to solve as well, this is what the distribution would look like. This is what the distribution would look like. You need a two-tailed test, so that means that the critical region is going to be split evenly between the two tails. In addition, you were asked, hypothetically, to test the hypothesis at the 0.05 level. That means that 0.05, that space, that's area, that's the size of the critical region. That 0.05 level or 0.05 area, that 0.05 amount, needs to be split evenly between the two tails. So each tail is each tail takes up 0.025, 0.025. If you added them together, 0.025 plus 0.025, you would get 0.05. Also, if I know that that the tails together equal 0.05, if I know that the tails together equal 0.05, I know that this piece in the middle has to be 0.95. 0.025 plus 0.95 plus 0.025 equals 1. All right, I'm going to cut this segment off and then move on to another example.